Anyway, hi, I'm Hana, and I'm having to talk my favorite data structures, kinda, because when I was asked for this like abstract, I actually didn't know what I'm going to talk about, and I drift significantly. So, I'm Hana. I work for Women by Toyota. uh, I'm chair of Reflection and Compile Time Study Group in C++ committee. I'm co-chair of Evolution Working Group, where all the fun and shouting is happening. And in past, you probably saw my talk about CTRE, at least one. I also did last year talk about Kokoro, which is like coroutine wrapper over Koro. And there is also library CT-hash to calculate various hashes in a compile time, and also create some encoding like base 64, base 32. So, but recently I'm hacking Clang because I want to fix things which bothers me. Hi Chandler. Also, I want to learn how things are implemented because I didn't know. I was kind of surprised and scared. And also to implement some changes in the language or prototype them, because why not? So constexpr is my favorite topic. I think everyone here is for constexpr. So in Clang, there is part called expr constant, which is Clang C++ interpreter. So you can actually interpret C++ constexpr. Are you raising a hand, Jason, already? Okay, it's in one big file. And I'm not going to say any like blah about it, but it's one file. It's 17,000 lines of code. And it's complete C++ for constexpr implemented in one file. I hate it. Chandler hates it too. And it's independent of UCP architecture, so it will work same on array architecture. And also it can emulate different, if you like targeting for different architecture, float operation will match your float operations on your target machine. And it's implement C++ abstract machine. That's important because for the rest of the talk. And it follows expr.constant part of the standard where like actually there is a list which it cannot do. Like you cannot do reinterpret cast. So constexpr is defined by removing things from standard. Everything else is allowed. So actually writing a paper to improve constexpr is actually like removing one line for one feature, another line for other feature, and convince other people to actually vote for it. So everything is in constexpr is symbolic execution. Forget about your CPU architecture, especially you, Patricia. Forget everything you know about pointers. Pointers is not address. And forget everything about values and memory. Because like, what's the size of number? It's a symbolic, it doesn't make sense. So, what's the value inside of Clang and symbolic interpreter? It's an AP value. And I didn't know what the AP means. I needed to ask Eric. And Eric told me, I don't know. I think arbitrary precision, and he's Clang developer for a long time. Yeah? Yeah, Chandler says that, right. And it's kind of like variants. So it can have multiple types inside, like type of values. So by default, it's initialized, it's none. Then it can be integer. And it can be integer of any precision on a bit size, not just 64, but like 256 if you want. It will make it work for you. You don't need to care about it. It's just number. It can be float of arbitrary precision. It can be fixed float. It can be array of other values. It can be structure of other values. It can be union of other values. And it can be L value, which is pointer or reference, pointing at something, some other value, like something. So, what's an array in Clang? It's a structure of three items: size, capacity, and data. An array of actual values. It can be partially initialized. It can contain different values because AP value, each of them can have different value. So you can initialize it like this, and that is size and capacity, and it's growing, but it's fixed size. But the union, and actually I didn't know what time code. Okay. Union is another structure of field and value. By default, it's empty, initialized, but if you want to put int, you need to have union in your AST, and the first field will point at the AST element of the field integer in ID. If you want to put float, it will point at other field in the AST or any object, and then you will put the object inside. This is not pointer. It's like it's inside. My animation engine cannot do things inside yet. So structure is similar. It's a structure of 3 items. Structure is structure. Number of bases, number of members, and data. So in this case, we have structure position, float x, float epsilon, and structure circle, which is inheriting from position. It has radius and color. So first item is the structure of position as the base. Base is always stars. And then it's the float of the radius, and there is the another structure with the color, which is something we don't need to know. And no value has a size. What's the size of color? You don't know. I don't know because I didn't put on the slide. But it doesn't matter. So what's the pointer? Patricia, what is pointer? Exactly, there is no pointer. But we can point at something. How? Address? Do you think it's a good idea to put a raw memory address into pointer in symbolic interpreter? What will happen if you point at something and then you destroy it later or unallocate? It will dangle, and you don't want to dangle pointer because it will crash your interpreter. You want to detect it. So it's some sort of identifier. Yeah. Okay. So what can be pointed by a pointer? Can you point a value? Value doesn't have any position in or anything. It's just a value. So you need to point. It can be something, obviously nothing, but you can point only on object, on something which has a name or some meaning. It can be initialized. It doesn't need to be initialized. You can point on an initialized object and it's fine. You can point at normal object, which is initialized, or you can point at array or its member, like this. Okay, you can point behind object, initialized, or behind array. And it's special type of pointer. It doesn't point anywhere, but it has semantic meaning. It's behind something. It's in this case, it's array of objects called C. So it's C behind $, like regular expression. Therefore, it was like behind object B, behind object A. So also, because everything is a symbol, there is no ordering. You cannot order pointers. So if we how we sort this? What's the first item or first object? Sorry. By its value, by its position in space. Maybe it's just 1D space. We can order it, but maybe it's 2D space. Or I don't know. It doesn't have any value we can sort. Okay, so that is a thing. You can compare pointers if they are in same provenance. How many of you heard about thing pointer provenance? 1, 2, 3, 4, 5. Chandler, are you raising hand or not? I want to on the record. Okay, yes, Chandler is raising hand. Okay, so let's have structure of item, which is like 3-dimensional position of 3 members, and we can represent it as object with first member, zero member, first and second. So it's inside one object, and there are 3 sub-objects. Sorry, it's like low because I need to put everything on top, so I hope you can see it. Then we have another structure, items, which contains up to 8 items, and also count of them. And you can represent it like this. Is everything okay with this? We have like array 0, 1, 2, 3, 7 and count. Patricia, is this right? Patricia doesn't know. You can point at behind array and also count. In your world, it's same address. In my world, it's not. In my world, these 2 pointers are completely different. My world is secure. So no, this is not right. So actually, items is one object of data and count, and inside of data is array of 8 items. So, and there is another type, universe, which contains only items. Just I needed something on top of it. It's structure of one member. So if I have object allocated or named a, variable a, of type universe, the name points at the object itself. But if I want to look at the sub-object, I can have pointer on the items, and I mark it a.0. And from the provenance, I can go only down. So if I have a pointer at the items inside the universe, I cannot go to any other member. I can go only down. I can also point at the and behind the universe if I want to have like a range, and so it's useful. But let's go into items. So I can point at count inside of items. It's a.0.1, and I have pointer on int count and nothing else. I cannot go to the left to right. But if I look at the data, I can look at the members of the array from the provenance. So I can go there, and from there I can go to item t, like this. I can go also behind item t, but I'm still not going to second member. I'm still at 0th member. What's happening? Huh. I can go back, but not like from the pointer. I need to go back, and then I can point like this. And always the provenance is only like can take me down. And if I'm inside of array, I can go also to other members. And also I can go behind the array, because if I want to pointer starting from first element to the last element, I need to pointer behind the last element. I can point at the items t behind, and it's different provenance than this one. Okay. What's the difference between L value and R value from Clang interpreter point of view? One is on the left and one is on the right. From the interpreter point of view, there is no difference. It's a part of the code. Only difference from our perspective for R value is just it's different pointer or reference, but it's marked as temporary. It will be soon destroyed, and you can safely take something from it. And in C++, there is no thing like moving something. You're always doing copy, and it can be cheap or expensive. Copy usually means expensive copy, and move means cheap copy, like stealing pointer. So lifetime, because if something is temporary, we need to talk about lifetime. So we have global variables. It's a pyramid. Global variables and constant. And from the left to the right is like lifetime of your program, kinda. On top, you can have scope-based variables, which is variables in your function, in your blocks. Then you have temporaries, which are parts of your expressions. Compiler will create them to evaluate your expressions, and it will destroy them at the end of the expression. And you can have custom allocations inside of the expression. You will allocate something, and because it's custom, you can do whatever you want, so it will maybe leak. Also, temporaries can be extended. If compiler sees that this temporary is pointed somehow, there are rules and I'm not sure about them because they are hard, so it can be like that. Okay, so identifier, or what we are pointing at, it's its location. Global variables are identified by its name, AST node. Local variables are identified by AST node and version. So if you go again to the same variable, compiler can actually detect its different value there than you expect and can detect error. I don't know actually how to trigger it, but that's how I see it. I'm right, Chandler? Yeah. I mean, all this can be totally wrong because I did archaeology in Clang and tried to understand the code from reading the code. So take it with a grain of salt. And allocated values are identified by unique key you get with allocation. It's actually counter of your number of allocations. So let's have value of two integers, a pair, and we want to point at it from somewhere. We need in pointer, we need two things. We need ID of the thing. If it's stack based, global based, or allocated. So in this case, it's local variable inside a function. It just points at the AST node because compiler has the AST of whole C++ program, and there is somewhere variable in it. And provenance. In this case, we are pointing at first member, so provenance is .0. And if it's allocated, we can put their allocation ID, and it's different type of pointer to allocated thing, and the interpreter will find it for you. So constant evaluator just walks AST in Clang at least. It's nothing fancy. You have AST tree, and it's just going into it as you would imagine. And if there is operation plus, it will look on left operand, evaluate it, on right operand, evaluate it, put them together, and return the result. It's the most naive approach you can do, and it works. And this is all implemented in C++. And it has funny consequences, because if you want to implement some feature, usually the best thing to implement a feature is the feature itself. So do you want to implement exceptions in constexpr? Exceptions would work best. You want to implement coroutines in constexpr? You need coroutines probably. So it's confusing. You don't want to put something into integer because that's what my heart says. Just put it in integer, but you need to put it into AP value. So my starts in Clang were kind of really confusing. But it helped me understand abstract C++ machine much better, because constexpr interpreter is just kind of extreme interpretation of the abstract machine, which is almost one-to-one mapping. So it can detect any violation of the abstract machine, and any violation is usually in your land, again, security issue. So if you can write your code as a constexpr and test it for all the possible inputs in constexpr, or the at least border conditions, and compiler won't tell you anything bad in it, then your code should be safe. And Chandler is raising an eyebrow. That is the star there. So most of the standard libraries should be constant available. Do you agree with me? I mean, it's a standard library and it should be used in every C++ variation there is. So it should be also usable in constexpr. I want to use string in constexpr. I want to use arrays in constexpr. I want to use mathematical operation. I don't want to implement them themselves because they said that standard library is supposed to be things which are hard to implement and easy to make it wrong. So they should be there for you, usable also in constexpr. I know some people don't see a value on writing constexpr code, I do, because you can pre-calculate anything. And if you can write everything in constexpr, you don't need to have like two implementations of same thing in your program. One is constexpr, one is not. And doing like if constexpr and if const eval and do something like else, because language rules won't allow you. So, but most of the library is not. And it makes me sad. And you should too. So let's talk about containers in standard library. And it's a quiz time, so I expect your interaction. Is array, that array, constexpr? Mostly? What do you mean with mostly? Array is constexpr. Yes. Good. That was easy. It's constexpr since C++11. Deque. You are right. How many of you are using deque? Deque intentionally or via container adapter? Because if you use stat stack or stat queue, you are using deque. Yeah, some people do. Flat map. It's a new thing in standard. There is one voice saying yes, constexpr. Someone in behind is showing like this, Jason Turner. It's not. It's a new thing, and it's still not constexpr. Flat set, same thing. Forward list, the most easiest structure you can implement. I expect you answers because I'm not going to forward. Okay, you are right. And it's sad. In place vector, a new thing we added just recently. Yes, with star. For constexpr types, it needs to be default initializable. Because it's using underling array, and array needs to be allocated if it's on stack. Hive. It's going to be in standard. It's already in library, so it should be in 26. Hive is data structure which gives you pointer stability. Your item will never move. And also give you like mostly the stability. It's useful for network programming and game development. And in the paper, it's I think revision 28 or something. The author says, yes, I can make a constexpr, but it will be much harder, so I'm not trying. List. List should be constexpr. I'm so disappointed. Map. No. Set, obviously no. It's same container. Basic string. Yes, it's constexpr with caveat. Unaltered map. No. Another set, obviously, also no. Val array. Jason Turner things. I mean, it's mom, we want simmed. No, we have simmed at home. Val array. Yeah, it's not. Vector. Yes. At least something. We need to look at some details in the in containers. Set array is constexpr. It's just array wrapped in type, and in template it's constexpr. Vector, it's just 3 pointers. You allocate storage. You have begin and capacity. You can add something into it, and when it's full, it will allocate new storage, move items from it, and then deallocate it, and you have some space to put new things again, and it goes like this. It will never shrink unless you ask it to. Stat list. Stat list is not constexpr for some reason, but vector is. And list is just allocating node. You have front back, you can insert behind it, you can insert behind it, or you can insert in front of it, with O1 complexity. And it's not constexpr. Do you have any idea why? Chandler, it's you were still there in the committee. Do you have any idea why? Yeah, you can erase items also. It's easy and it's super easy algorithm. Everyone here in a room, I believe, can implement it as constexpr. Okay, in place vector. It's using array and it's not constexpr because you cannot have initialized element in the array. And we are still trying to find out how to bend rules to allow it somehow, like mark it set initialized or with some attribute or using some union tricks. But if you put union into array, suddenly pointer at the item in the union, because provenance is not able to jump to next item in the array, so it's not contiguous storage suddenly. And I think in place vector should be contiguous. At least people would expect that under this name. So do you want contiguous or do you want constexpr for everything? Yeah, I can put stuff like this. So it's not constexpr. Deque. This one is not animated, sorry. On the left you have prefix on the top and suffix on the right. And there is index structure, which is just a vector of pointers at leaves. And leaves are always fixed size. And you put on front on right by O1. And yeah, that's all. Deque is simple data structure. Just by diagram, it should be constexpr. And it's not. So these all seems implementable. And I see Bryce, so we can blame Bryce. He was chair of library evolution, so why is only vector and string constexpr? Because these are like important for someone. And it cost me chocolate to put it into the last possible slot in library working group to 20. But language is improving with every C++ version. And in past, some of these features, like allocation, were not available in constexpr. So it kind of makes sense, but library is lagging. So sorry, Bryce. And so constexpr limitations, another quiz time. Oh. Atomic operations, can you use them in constexpr? Someone is like nodding like this, someone's like nodding like this. Not yet, no. Changing active member of union. Yeah, that's a new feature of 2020. I think 20, yeah. Yeah, 20. My slides know better. Control flow with if, for, and while. It's 10-year-old thing. C++ 14. So C++11 didn't have control flow operation. Everything was able to done via condition operator, which work. I think it was like people overlook it when specify it, but it worked, and that was the reason why we got if for while later. Exception throwing. No. I think I need to ask how many of you like exception. I also like them, by the way. Good. I like it too. Lambdas. C++ 17. Trivial default initialization. Sorry. So you cannot, you don't need to initialize every constexpr variable inside constexpr because it will be trivially initialized for you. 20. 20. 4 years ago. Try catch. I see some frowning, some not like. I'm not going to like look at you because you know, but yeah. Yes, but you will never go into catch handler. You will just enter try handler, and if you run into any exception, it will stop the constant evaluation at all, like totally. So yes, unevaluated inline assembly. Patricia is shrugging. 20. If it's not unevaluated, it can be there. There was a shift in constexpr. I think in past it was supposed to be always constant available for everything you can put in it, and we slowly drift into it can be constant evaluated for some inputs and for some paths. So I think the requirement for constexpr is like weakening with every standard, and hopefully maybe in future maybe it will go away and everything will be available if it's visible. I don't know. That's my wish. I had paper and it burned quite well. Usage of variables inside of constexpr. It's obvious that yes, but in which version? So no, Jason, there is no 16. Yeah. 14, yes. Using byte array as object storage. Trick useful for like stud function and other like polymorphic type. What do you think? Sean, what do you think? Yeah, no. I want it, but it's hard, and I talked with Richard Chandler how to make it work somehow magically by stealing the first AP value, put it there, and make all the AP values like no, there is nothing to look for, and I have magical function which will allow you to access the new value like set lambda. Valid reinterpret class. There are some use cases for interpret class which are valid by standard, and like you can take pointer to char and convert it into object because it's byte array maybe, or you can reinterpret cast if you have trivial type and you have pointer at first member, there is specification that you can actually go to its parent type, or like to its owning type inside, and it's actually used in senders and receivers. There is like union with byte array, and there is an object, and from the object they are taking pointer to the union, and from the union, because it's first and it's trivial, because it's a byte array, it's not type, they are going to their parent object, and because the parent object is parent like in class for child, they upcasting to the child. Yes, yes, yeah. That was my exactly I'm trying to make everything constexpr, and when Louis told me about this, I was like, no. Sorry. And virtual basis. You can have virtual basis. Chandler says yes and no. We can have virtual functions, but not basis. Because someone didn't specify it, or someone didn't scratch the one paragraph saying you cannot have virtual basis, and someone didn't implement it then. So yeah. In future constexpr improvement, I have few papers. When I was supposed to working on these slides, I was procrastinating a lot. So I wrote a few papers. For example, allow exception throwing in constant evaluation. It's already in core and in library evolution, library wording group, and you can throw exceptions in constexpr. And it's actually nice to give you a nice error message outside of constexpr evaluation without bothering you with long stack trace. If you are just a user of the library, for example in CTRE, I would be able to give you a nice error message. You provide a regular expression with wrong syntax. You don't need to know from where the exception was thrown. Pointer tagging. Because pointer is just data structure, and in Patricia world, it's just bytes and address. And not all bytes are useful and used. So you can use them to store other value. And it's use technique even in Clang itself. There is a thing called in pointer or pointer int pair. And so you can have pointer on something, and two bits from alignment, which are always 0, are used to say what the thing is. And there is a cast, so you can have like pointer at something or something, and it just 8 bytes or 4 bytes, and it saves some space. And it's useful technique. But I want to make it also in constexpr. But in constexpr there is no address. So actually the bits to store the information is just some sort of metadata inside of a pointer. Constexpr atomics and atomic ref. I mean, no one will write in foreseeable future any multidated code in constexpr. But you should be able to use same code, some algorithm which takes like, give me one item from some queue or some like array to process. So atomic should work in constexpr, because constexpr is just an implementation of abstract machine, single threaded, and atomics work in single threaded environment. So it should work. It's just a normal operation, but you don't need to write if const eval and just to work for you. So magically. Containers and adapters. Every container and adapter should be constexpr. I have paper for that, and I run into some issues. For example, you cannot compare pointers, obviously, as I showed you with provenance. So you cannot put as a key into map pointer. You need to put something else into it. Also, you cannot hash pointers based on current rules. You cannot have stud hash of pointer, because hash inside constexpr is a symbolic, like pointer is a symbolic address, and in a runtime it will be different, even if it's like same object, because it's subjected to linker or optimization. So you never know, and the hash will be different. So you can also hash adapters. So under that map for keys with pointers won't work, but for everything else will work. Constexpr, all the exception things. Jason, I was like inspired, and it's just making all the constexpr objects and exceptions constexpr. It's just marking all the .wat members constexpr, and they usually just return string literal. So there is nothing controversial, but it's house cleaning. Constexpr coroutines. I have them partially work, and it's beautiful. You can write stud generator in constexpr and use it to fill some structure, and it should work because it's obvious. It's just like the wording itself is actually scratching 2 sentences in full standard, and everything should magically work because nothing is specified in a way it shouldn't. So only these 2 sentences are actually forbidding us like to have it. So what's my favorite data structure? It's also my motivation for all this, because I found recently, it's a while ago, data structure which I really like, and I want to be able to write it in constexpr. And there is a few things which bugs me, and I need to fix them first. You need like the light bulb broken, so I need to fix something and something. It's called AHMT, hash array mapped tree, and it's all cool things in one. So what's happening here? Something is broken in my presentation. Oh, what's happening here? No, it worked just before. Okay, I'm sorry. I was finishing this presentation, this slide just before I went here. And technically, when you have a tree, like set map, you compare them against ordering, and it's always O log n operation. If you have another map, it's O1 at best operation, but map grows linearly, and another map grows you need to rehash everything and grow it, so it's growing like every time when you it grows, it's linear operation. So hash array map tree is data structure which grows as stat map or as tree, but also it's giving you O1 operations for searching, inserting, updating, removing. And it works like this. You have a value and you hash it with a hash of 32 bytes size. And you take each 8 for depends on the configuration. And so let's say you take first 8 bits and its position in first level node. So if like first level node is 16 items, 16 is 2 to the power of n, 8. So if like 16 items on the first level, and first 4 bits or first 4 bits of the hash is, let's say, 3. So you will look at element number 3. So it's O1 operation, and then you will look on next 8 bits, and you will do some part of the hash, and you go like this, and you will always do number of operation which depends on size of the hash, and the size of the hash is constant. That's kind of cool, but you can do better. If you use pointer tagging for the pointers inside of the node, you can actually say if it's node or leaf. And if it's a leaf, if there is only one leaf in your subtree, you can just skip it and just put a leaf there. So it's O1 and or O1. Better O1. And yeah, and you can do even better because the nodes are like 16 pointers, which kind of large array. You can put a bitmap in front of the node and use only have the nodes of size of actually only n nodes you need, and bitmap will tell you which node is enabled. So if you have like 4 bits in the bitmap enabled, in your node there will be only 4 items, and the size of the whole node will be smaller. And I had animation. Like, wait a sec. I will try to open it Safari, because I'm using some feature in the presentation which is supposed to be in Chrome release today, but not yet. So yeah. Okay, so we have root, and we have some item. I'm using only 16-bit hash because it's so I can put it in slide. So I have like item on the top with some hash, and we have top level node, and inside of it there is a pointer or position 4. 0, 0, 1, 2, 3, 4. Then on the next layer there is a position on E, which is 15. On next layer it's on position 8, and on next layer it's on position F. It's just like you just go like this, but you can do better. You can have compressed nodes with bitmap, and only pointers to other items somewhere else. I don't care about it. There is maybe only 1. There's like 4, and there is only 1, and there is the value. So you need to do pop count and convert all the lower bits which are not yours to actual position in the node, and you will select the right subnode and just go like this. It's beautiful data structure. It grows like map, and it shrinks. you remove something. And also it behaves as a hash table. So you will never need to rehash it. Chandler, do you like it? I know your hash table is much faster than everything else, and why don't you like it? Okay, you can like, yeah, I like this, and I don't like you. And that is even better. If you added it into Node, I don't have animation for that. If you add it into Node, also ref count, you can make this data structure persistent. So you can have multiple version of it, sharing all the common data nodes. So you need actually constexpr atomic operations for that too. So requirement for the language I want to support this is pointer tagging. So you can actually compress the like depth of the tree. Variable sized objects. So I can have variable size. It can be done with allocation. So you can actually allocate like array, and there are some tricks for some costs, but it can be done. But somehow we should also allow this. Atomic operations, if you want to make it persistent, so you can actually have ref count how many other like nodes are pointing at my node, so you can ref count, and if some tree is destroyed, it will destroy only the nodes which are not there. Oh, what happened? And byte storage for objects, which is other approach for the variable sized objects. But also, there is a thing, you don't need pointers, Chandler. You can actually write all this into a flat storage, into byte array, and always append. You will always, on every write, you will append, and instead of pointers, you will use offsets. They can be shorter, and suddenly you have transaction log with data structure. So you will always append, and if you have also ref count there, the root is always at the end, so you can have like, if you have subspan view to the array, you have one version, and then you have another version based on the size of the subspan. So you can actually write it into byte array, so you don't have any pointers at all. Chandler, is that okay for you? Still no? What can I do? Okay, it's my favorite data structures. Thank you. If you have any questions, you are shy, you can approach me. If you are Norwegian, you can approach me too, because you are shy, obviously. And the audience gets better every year. Okay. If you have questions, approach me. If you want to ask here, we can do, but